Mars Landing Project by Lydia and Alina. For this project, we had to create a parachute and lander that would accurately land on Mars and keep 3 eggs from cracking.
Our parachute design was unique in many ways. We tried to make it as symmetrical as possible, meaning that all the strings were the same length of 70 centimeters. This was to help with the accuracy of the landing. Along with this, we cut a proportional hole in the center of the chute to also help with the accuracy of the parachute.
For our Mars landing project, we were challenged to create a parachute and a lander that safely landed 3 eggs, or astronauts, on the surface of Mars.
When we were designing our parachute, we knew that if we wanted to maximize drag, we also needed to maximize surface area. Within the parameters given to us for the size of the chute, the shape that gave us the most surface area was the square.
When thinking about our design for our parachute, we decided to cut 4 sides out of the corners of the trash bag, making a cross. We did this to make a zero glide ratio so that the parachute would not fly away and rather land straight down on the landing platform. We used 2.
In this Mars landing project, we were challenged to design a parachute and lander to land 3 eggs representing astronauts on the surface of Mars.
Our original design was a circular design for the parachute that had an overall diameter of 75 centimeters. It is attached to 4 strings, and each string is 45 centimeters long. The design of the chute was intended for the goal of creating as much air resistance as possible.
My name is Trevor.
I'm Oscar.
And together we designed a parachute to land on Mars.
This is our parachute design. The parachute was 50 centimeters in diameter and had 8 strings that connected it to the lander. It also had a hole in the center to guide it down to Mars.
Diagram of our parachute and our lander. Our parachute was 75 centimeters by 75 centimeters with a 12 centimeter hole at the top.
Was made with a big cylinder designed in the middle with an 8-inch diameter, and an open face on the top was constructed. Around the inside of the cylinder, 10 smaller cylinders with 1-inch diameter, and then within the empty space directly in the middle, you can't see it on the screen, but if you were on a bird's eye view, you're able to see, is the crumpled newspaper was placed inside. And that allowed for the force to be exerted on the astronauts to be extended throughout a greater time, which thus decreased the force. It also cushioned any horizontal movement when the lander fell to the surface, which allowed more safety for the astronauts, and it provided more cushion, which increased the time of the impulse and lessened the force.
Our lander design rationale was designed to give as much squish under the eggs and also give some protection on the sides. That's the squish. The squish was so that we would have more time in our impulse, making the force exerted over a longer period of time at a lesser strength.
This is the motion of our parachute from the distance versus time graph, and as you can see here, we start with positive acceleration, then we curve off a little, go to negative acceleration, then it increases again, goes to positive acceleration, and then we reach terminal velocity.
The section highlighted in red shows positive accelerating rightward velocity. After that, the parachute went outside the motion detector range. Velocity time graph. The section highlighted in yellow shows rapid acceleration.
Time graph. In a velocity versus time graph, the slope is equal to the acceleration. From the velocity time graph, one can infer that after the parachute and cup began to fall, it started to have a positive acceleration of 5.61 meters per second squared. At around 3.7 seconds, our parachute started to fluctuate, and the average of the fluctuations was our constant velocity, also known as terminal velocity of 2.26 meters per second. While at terminal velocity, the acceleration is 0 because the slope is 0.
Newton's first law can be applied to the parachute in many different ways. First, our object is at rest when holding it above the railing. It has a change in its state of motion when an outside force, gravity, causes our object to move from rest. However, for a light moment, the cup stayed at rest in the air, even after it left the hand. This is due to inertia, the tendency to stay in the same state of motion.
Newton's second law. This law states that the acceleration of an object is dependent on the net force acting upon the object and the mass of the object. The net force acting on the parachute was the air resistance pushing the parachute up and gravity pushing the parachute down. This is shown in the equation, which is net force equal to mass times acceleration. So we have our equation of Newton's second law. Net force of an object is equal to the mass times the acceleration. So basically the net force, we can see, is just the force of gravity minus the force of air resistance. And so to find the force of gravity, we have this equation. The force of gravity is equal to the mass of your object times the force of gravity. So we know that the mass of our object is 0.343 kilograms and gravity is 9.8. So we multiply these, we get that the force of gravity on our object is 3.36 newtons.
Finally, using the force of gravity and the net force, we can find the air resistance, which is 1.6 newtons. Here, we have the same process, but we found the force when it's at terminal velocity. Instead of the 5.03 velocity we had when it accelerated, we have 0 now. We solved this and got 3.3 newtons for air resistance.
Newton's third law states that for every force exerted on an object, there's an equal and opposite reaction force. And this one's pretty simple when it comes to the lander and the design of the parachute. Basically, as the lander falls, it exerts a force on the air, and in return, the air pushes back with an equal amount of force on the parachute and the lander.
And then our final example is the parachute pushing down on the ground and the ground pushing up on the parachute. And just one more time, these are forces are equal.
Third law states that forces exist in pairs.
It would.
Every action has an equal and opposite reaction.
Yeah, that's right.
This occurs multiple times during the landings.
Oh, yeah.
Such as the air pushing on the lander and the lander pushing on the air.
Uh-huh.
And the lander pushing on the ground and the ground pushing back on the lander.
No way.
Impulse. Impulse changes momentum by increasing the time an overall force is applied. I equals P. Impulse equals a change in momentum. The variables here explain what the more force equals less time, while the more time equals the less force. The goal of ours was to create a lander that maximizes the amount of time a force is applied while landing on the surface of Mars. We wanted to do this so that the astronauts could live and we could succeed in our mission.
This slide is about impulse. Impulse is force times time. The parachute creates more air resistance, and this increases the time that the lander fell. This increases the impulse and slows the momentum. And here we had the calculations that we used to find what the initial velocity of the thing was, which we found out to be 2.7 meters per second, which was very close to one of the graphs that we had earlier. And this is over here, this is our force versus time graph.
Perfect landing.
Love a shoot. So this is our bonus feature, and it's a parachute in the shape of a heart. And
Then our lander design was exactly the same, and we put some duct tape on our parachute to, stiffen up, make sure that the heart doesn't break.
And it's alternating silver and white, and it has some hearts on it, as you can see here.
And it has our slogan of delivering love to your doorstep.
So we hope you enjoy.
3, 2, 1, blast off to Mars.